Hello everyone, thank you for joining us for the Azure SQL Path to an Intelligent Database session. We use this title because the engineering team in Azure SQL and SQL Server have been working on several features in the intelligent database space over the last few years. We're still walking down that path. We're still continuing to invest in capabilities that automatically and adaptively improve performance and scalability. And as we speak, we have several new engineering efforts underway in the intelligent database space. And I'm happy to say we'll be able to talk about two of these new investments, and those will be landing in Azure SQL in 2021. So we'll talk about that today. Now, before we begin, just a reminder to explore everything that PASS has to offer. That includes training opportunities, networking, user groups, and volunteer opportunities. And also a reminder to please share your feedback and visit the session evaluation link on the left-hand pane to rate the session when we're finished. In terms of introductions, my name is Joe Sack, and I'm a program manager at Microsoft in the Azure SQL Database team, working specifically these last 4 years on the intelligent query processing feature family and also some upcoming query store investments. We have several engineering team members who help build the features that we're talking about today. As a program manager, our job is to be the voice of engineering, and with engineering, our job is to be the voice of the customer. And I'm joined here today by my colleague Pedro, who will introduce himself and then go over today's agenda and also a brief history of intelligent database features.
Thank you, Joe. My name is Pedro Lopes. I'm a program manager in the Azure SQL Server team, with my main focus being on the relational engine, which includes the query processor. In the last few years, the engineering team has been dedicated to delivering new capabilities to the engine that allow us to have further insights into workloads that are executing in the database engine. This includes enhancements to show plan, commonly called the query plans, but also lightweight profiling, less execution profile, and a number of other features that really lay the foundation for many of the insights we need to build an intelligent database. So without further ado, this is our agenda for today. We'll be discussing a brief history of intelligent database performance, which in other words means where we stand today in terms of the path that Joe mentioned towards the world of an intelligent database. And then we're going to spend the bulk of our time talking about what's next. What is the next step that we will start previewing in year 2021? Joe will talk about query store hinting, and then I will talk about a new feature that builds upon that capability, which is called CE feedback or Cardinality Estimation feedback. In terms of intelligent database performance, in the past few years, we have been focusing mainly on delivering features under the intelligent query processing feature family. With intelligent query processing, critical parallel workloads should improve when running at scale while remaining adaptive to the data that changes in the databases. The intelligent query processing principles are simple: to be available by default when using the latest database compatibility level, to deliver broad impact that improves the performance of existing workloads with minimal or zero implementation effort. For the overwhelming majority of the features that you see on the screen here, to use them, you just need to move to the latest database compatibility level. There is zero code changes required to make use of these features. But by making use of those features, critical parallel workloads should improve when running at scale. And as I said, remaining adaptive to data that comes in and out of the database. Now, by having the same database engine across SQL Server and Azure SQL Database, we can meet your modernization needs where you want to be. If you are on premises or if you are in Azure, you know that you have the same database engine and you have the same capabilities. This consistency across platforms means that you have predictable performance with the help of features that you see on the screen here. For example, memory grant feedback adjusts the memory grant sizes to learn and improve memory usage over time. The feature can adjust memory grant sizes for both batch and row mode operators, and will eliminate the effects of either grant misestimations, which in fact will mean that you spill to TempDB and therefore add the overhead of I/O, but also corrects the effects of overestimations, which will have a nefarious effect on concurrency of your database. For example, table variable deferred compilation improves plan quality and overall performance for queries that make reference of table variables. The database engine, what it does, it delays the first compilation of these statements that one or more table variables are found, so that the engine can use the actual cardinality, the actual number of rows of those table variables to generate the query plan, instead of using a fixed estimation or a guesstimation of just one row. This usually results in improved plan quality and performance just out of the box. Or scalar UDF inlining. Now, using T-SQL UDFs is an elegant way to achieve code reuse and even create modularity across your SQL queries. You write once, you use many. UDFs may help in building complex logic in this modular fashion, and you don't really need to be an expert in tuning large complex queries. However, using UDFs can also be problematic for performance, as we found throughout the years, mainly because there's no cost estimated for executing scalar UDF calls from a query. Even though we know these calls are executed iteratively with each row, the engine doesn't really know the cost of executing that. And because these are not realistically costed, they can, for example, prevent a query from executing in parallel, which could otherwise become a significant performance boost for some workloads. This feature improves the performance of queries that invoke scalar UDFs in the database engine, and again, without any code changes. So as you see on the screen there, the features that are indicated in bold, those are new features or improved features in the latest iteration of SQL Server and as expected in Azure SQL. The ones that are not bold were introduced earlier in terms of SQL Server back in SQL Server 2017 and at the same time in Azure SQL Database. So for now, you see that there are numerous aspects and numerous scenarios that have already been handled by these features, which can work in tandem with each other. These are not mutually exclusive, and they can all work adaptively and automatically to improve your workloads. If you want to know more about each of these features, please refer to the short URL you see on the screen there. And to play with these features by yourself, either using self-guided demo scripts or fully annotated SQL notebooks that you can use in Azure Data Studio, please refer to the short URL that you see there, aka.ms/WAC-IQP demos.
Okay, next we are going to talk about a new feature that's previewing in 2021 in Azure SQL Database, and we call it Query Store Hints. Now, this is part of an overall wave of new features that the query processing team is working on. Wave 3 is what we're informally calling it for intelligent query processing and also query store related features. And this will be one of the features previewing first. And before we get into the actual functionality, I want to talk just a little bit about query hints. So ideally, when you have a query and you execute it for the first time, we select an optimal execution plan quickly and you're happy with the performance. But when that doesn't happen, a DBA or a developer may decide that they want to manually optimize using query hints, and it affects specific conditions in your query. And you can use an option clause in your actual query. The example you see on the slide here is a select count distinct from a fact table. And you see that I'm using two different hints. One is a disallow batch mode hint, which says don't use batch mode, use row mode execution. And then the second hint is a recompile hint that says we don't want to reuse the plan. We're going to go ahead and eject it as soon as we're done with it. We're going to actually compile from scratch. Now, that's all well and good, but it can be difficult to actually get a hold of the original T-SQL that you need to actually intercept and add the query hint to. So DBAs often can't make changes to the original T-SQL code. It might be embedded in the application if it's not in existing store procedures, or it could be automatically generated by an ORM or elsewhere, or it might break your ISV agreement to have direct change to the T-SQL code. And today, and for several versions going back into the past, DBAs have the option of plan guides, but plan guides haven't been updated in a while, and the overall and recurring feedback we get from customers is that plan guides are pretty complex to use. So we're introducing something called Query Store Hints, and the idea is we just keep investing in Query Store itself because it just simplifies the overall performance tuning experience for DBAs and developers. And so we're going to add additional functionality that will allow you to apply query hints to queries that have been captured in Query Store. And we want to make sure that it's a simple process. I have two slides, a step 1 and a step 2 slide. Step 1 is you just need to find out what the query ID is that you want to add the query hint to. And I have an example query here that I'm pulling from a TPCE workload. And I'm searching based on a chunk of query text. And I see that my query ID is 46,006, so 46,006. And I could have used SQL Server Management Studio reports as well. There's a number of different query store reports. In this example, I'm just using the catalog views. So I know what my query ID is. And now I also have a new system store procedure called SB Query Store Set Hints. And with this, you can set one or more hints. And first example, we have SB Query Store Set Hints, the query ID, followed by the string where I'm saying option hash join. So if it's, for example, using a nested loop, my query hint will make it use a hash join instead. You can also set multiple hints. That second example shows where I'm setting recompile, max.1, and then saying use query optimizer compatibility level 120. So a few different query level scenarios you might want to use with query store hints. One example would be recompiling a query on each execution, assuming you have the CPU headroom, being able to handle parameter sensitive plans by saying for this query, always recompile. Doing things like capping the memory grant size for bulk operations that get captured into query store. Limiting the max stop for specific queries, changing join algorithms, changing compatibility levels, or even advanced scenarios like disabling the optimizer row goal for a select top query. So lots of different ways that you could use this. And I'm going to go ahead and show you one example of using query store hints against a parameter sensitive plan scenario. So in this demo, I'm going to show a parameter sensitive plan issue. And to do that, I'm using a procedure called property search by agent, which accesses a table called property. And these are property listings that are for sale. And we have this input parameter of an agent ID, and an agent or an agency is associated with one or more properties that can be for sale. So depending on the agent ID that I pass in, I might get a few properties, maybe 3 or 4, or I might get hundreds of thousands or even more properties if it's a large agency. So we have this stored procedure that is sensitive from a parameter perspective, and if you cache the wrong plan, could end up giving a non-optimal plan for scenarios where you have a big number of properties for sale and the small plan is cached, or vice versa. Now, if we look at sys.dmdb_stats histogram for the stats associated with the agent ID, you're going to see the skewed distribution in the stats. So zooming in here, you'll see we have agents ID 1 and 2 have many different properties for sale, but you also have several agents that have just a handful of properties. And just scrolling down a little bit further, you're going to see one of the agents that we'll use in the example, agent 101, has 100,000 properties for sale. Now, if we hop back here, if I execute for agent 101, property search by agent, and I have included the actual execution plan, we're going to see what plan gets chosen given the fact that we know in the stats that 100,000 some rows are going to be returned. So we get 100,000 rows back, and if we look at the plan, just a few markers, we see these are thicker lines, we see parallelism is in effect, and the overall assumption here is that we're scanning because you've got many rows versus a seek operation or a key lookup operation, depending on what you're trying to do, might have been more optimal. And if I go ahead and I execute for property search by agent with 4, this agent I know only has 3 properties for sale versus 100,000. But because we've cached that plan, if you take a look at the execution plan, you'll see we reuse that plan. So now we've got this plan that assumes 100,000 rows, so but we only end up having 3 out of 100,000. And then this can lead to waste because you're now running in parallel. You have a larger memory grant than you might want. If most calls are for a small number of properties, then you have overkill for this particular query execution plan. So let's say you get called in the middle of the night about this and you need to help solve the problem and you can't rewrite the procedure at this time, or maybe you can, but it has to take a few weeks before it's approved to production. Well, as a temporary stopgap, you could do something like apply a query hint and use query store hints. So what I'm going to do is I'm going to query sys.querystore query text joined to query store query, and I'm just searching for the SQL text so that I can get a match on the query ID. If you prefer the user interface, you can use SQL Server Management Studio query store reports. I'm just showing the catalog view way to do things. So if I execute this for the query that we want to add a hint to, it's query ID 3. Now I'll grab that query ID 3, and I'm going to use the new system store procedures, the SB query store set hints with a value of 3, and I have my hint option recompile. Now, with option recompile, there are always trade-offs. So you increase the amount of CPU. If there's a high compilation time, you might end up driving up CPU overall. If you have a low amount of headroom for CPU, this might not be something you want to do. But in my particular example, I know the compile time is small. I also know that I have headroom, and I want to solve this issue because I'm getting paged at 2 a.m. in the morning, and I just want to solve it until we can actually revise the overall store procedure. So I'm going to execute this to add the query store hint, and then I can confirm that it was created in sys.querystore query hints. So we'll go ahead and execute this, and we'll see that we have a new entry for our query ID, our query hint text, and we also have failure reason information. So if for whatever reason we can't apply the query hint, then we'll give the query failure reason and description, similar to what you see with plan forcing. Now let's go ahead and re-execute both store procedures, one with many properties, one with only a few properties. And if I execute both of these, we're going to see that the first query that has 100,000 rows has the same plan. The second query now will have a different plan. So the first plan is what we saw before, where we have parallelism, we have the thicker lines, we're doing a scan. But then the second query now, because we're doing a recompile behind the scenes, we're seeing that, okay, let's use the low row assumption here. So we're assuming 3 out of 3 rows. We're doing a key lookup, nested loop operation, but it's really key lookup. We've got this skinnier line. So if you think about the memory grant size, it's going to be much smaller, like 1 meg versus the larger plan, it's 17 meg. So much bigger difference. And now whenever it gets executed, we're going to recompile each time. And again, until you can find other solutions, or maybe this is your longer term solution, depending on the frequency of how often that procedure property search by agent is executed. So as a final step, I'm going to execute SB query store clear hints. If you want to remove it, let's say you do make your changes and you want to remove the hint, you just execute that with the query ID. And then I can confirm that it has been removed through the catalog view. Sure enough, it's been removed. And if we re-execute both of these again, you'll see the previous behavior. So you're going to see we're going to first cache that scan plan with parallelism, and then the second execution for the low number of rows will reuse that plan. And so we're back to our original state. So now we're going to talk a little bit about query store hint scope and behavior, and just get into more of the details leading up to the actual preview next year. So query store hints will support statement query level hints in the first version, and they will be persisted, which means if you restart SQL Server or there's a failover, that those hints will survive the restart. Furthermore, the hints will override hard-coded statement level hints or any plan guide hints you have. This is similar to plan guide hints being applied as well, where it has the final say. And if hints contradict what's possible, for example, if you're asking for a join algorithm choice that contradicts what's possible for optimization, we will not block query execution, and instead we'll log that error in the catalog view, and then the query store hint will not be applied, and we'll go ahead and just execute your query. And this is similar to the philosophy for plan forcing for query store as well, where we don't want to block actual execution if it means that forcing is no longer applicable. Now you saw that we have new system store procedures. We have SB query store set hints, takes a query ID, and then it takes the query hint string, one or more query hints. And in terms of those hints, they're specified in the N option format that you saw before. And if you have a query ID that has no other hints associated with it, then we'll create a new query store hint. And if you already have a query store hint for a specific query and you're updating it again through SP query store set hints, it will overlay with the last value used for the associated query. And then if the query ID doesn't exist, then we'll raise an error. Now to remove the hints, you saw SP query store clear hints with the query ID, so pretty straightforward. In terms of the actual queries that we'll support as of preview, so initially for preview, most query hints will be supported out of the gate. So things like actual fast number of rows, loop merge hash joins, things like max grant percent, min grant percent, recompile, those will all be supported, as well as use hints. And there's a couple of exceptions for use hints, but the majority of use hints will be supported as of preview. A couple of things that will not be in preview, but we will target for GA. One is optimize for a specific value. Optimize for unknown will be supported in public preview, but as of the first public preview, optimize for with a value will not be available until general availability or late into preview. And then max recursion is another hint as well with that same circumstance. In terms of unsupported and not planned for GA at all, one is use plan hint, because we want explicit query store forcing capabilities to be used instead, for example, through SB query store force plan. And then second area is related to how we optimize actual use hints. So there's two different use hints: disable deferred compilation TV and disable T-SQL scale or UDF inlining. Now, most query hints are consumed in optimizer code while it's generating a query plan, and some hints like disable deferred compilation TV are consumed earlier during normalization when the query store query key isn't available yet. So in other words, the query hint is consumed at a point that precedes the usual hint code path in query store. So we don't plan on having those two hints supported as of GA for use hints anyhow. Now, beyond V1, we have a few different things that we're thinking that we're going to do. And of course, we're going to be listening to feedback over preview and see if there's particular nudges in one direction or the other, or different areas to prioritize that I haven't mentioned. But one area is having the ability to apply a query hint to incoming queries that haven't been captured yet in Query Store. Today's V1 will only apply to queries that have been captured. And what would the scenario be if we could actually pre-populate a set of hints for specific queries, like in a packaged app? Second is applying parameterization to a query that parameterizes to a specific form. That's something that template plan guides can do, and we would like to have that similar functionality for Query Store hints beyond V1. And then lastly, having the ability to do table hint support. So things like index hints, force seek, force scan. Now, as I've mentioned a couple times, we're looking at this for 2021 public preview in Azure SQL Database across all deployment options. If you want to follow Azure updates, you can stay tuned on when that preview gets announced. And of course, there'll be a blog post and updated docs and other artifacts out on the web that will let you know that this is coming. And we also have an email alias that you can use if you want to provide feedback or suggestions or just overall observations around Query Store hints. And it's qshintsfeedback@microsoft.com, and that will get to the team.
Another feature that we will be previewing in 2021 in Azure SQL Database is CE feedback. CE feedback, as you will see, is a feature that builds upon everything that Joe discussed just now. But to understand the CE feedback feature, we must first understand what cardinality estimation is today. The cardinality estimation is the process that the query optimizer uses to estimate the number of rows flowing through a query plan to provide the result set. This cardinality estimation has models, and those models are based on assumptions about how data is distributed in a table and the expected usage pattern for that data. This is thoroughly documented, and you can refer to that URL you see on the screen there to find more about the cardinality estimation process. What is important to understand is that the cardinality estimation is primarily derived from histograms. And those histograms are created either manually or automatically when we create indexes or statistics. The important thing here is that we know that the database engine sometimes cannot accurately calculate these cardinalities, cannot really accurately get the estimations for the number of rows flowing through the plan, and that in turn causes suboptimal query plans or inefficient query plans. In essence, we know that one model does not fit all scenarios. We had a set of models in C70 all the way up to SQL 2014, and in that version, we changed some of the assumptions for the model. But we know today that, like it's on the screen here, one model does not fit all scenarios. So that's why we are introducing CE feedback. The intent is to reduce the friction related to changing behaviors in cardinality estimation and reduce the risk of regression that comes from there. You shouldn't have to be an expert in cardinality estimation. You shouldn't even have to care about concepts that we are discussing here today, like independence or correlation or row goal. Because we know there is no single set of models and assumptions to accommodate all the workloads that you run out there, all the data distributions, any solution that we proposed to ourselves to introduce needed to be adaptable based on runtime characteristics. And that is what C feedback will be doing. The C feedback will learn about which assumptions are more optimal for a given query and apply those assumptions that are more correct for any given query that fits the profile. The scenarios that we will be tackling first are some that we know can cause most friction in those scenarios that you move from an older version of the cardinality estimation to a newer version of cardinality estimation and see perceived regressions. The C feedback feature will identify those model-related assumptions that are not perhaps working as well for any given query, evaluate for those queries if there is a different assumption that works better. If there is, after verification, then it will be persisted in the query store and will be from henceforth replacing the previously known plan that the query optimizer calculated. In essence, all this process will be based on the observation that actual row counts are very skewed when compared to estimated row counts. And there's typically that large skew, that significant difference that results in query performance issues. So what is the scope for CE feedback? We'll only apply feedback when we see a significant model estimation error. In other words, when the difference between estimated number of rows and actual number of rows is in orders of magnitude off. We'll also only be looking at repeating queries, so repeating workloads, whose plans stay in cache, meaning, for example, a trivial plan that typically does not remain in the cache won't be in the scope for C feedback. How will these model assumptions be adjusted? Well, they can be adjusted today through use hints. So what C feedback will do is, after running through the analysis phase and verifying, we'll be using those use hints through the hint supporting query store that Joe mentioned to be able to lock that better choice in terms of model assumption for that given query. However, if you are hard coding query hints, if you have your own query hints hard coded in your code and they conflict with any recommendation that C feedback has, your hints will prevail. So any user code that you have will prevail. Keep that in mind when you enable this feature. And like I said before, only verified feedback is persisted. Let's say, because this process piggybacks on your repeating workload, during the verification stage, let's say that the proposed hint actually does not yield a better result. It actually yields that that specific execution is regressed. We will immediately back off. So the do no harm principle is front and center here. So let's look upon the several scenarios that C feedback will tackle. The first one being correlation analysis. We have three possible principles in terms of looking at how data is correlated in a given table. Data can be fully independent, partially independent, or partially correlated, whatever you want to call it, or fully correlated. The CE70, or the old CE, quote unquote, assumed independence. Assumed that data distributions on different columns of the same table are independent of each other. That changed in CE120 to partial correlation or partial independence. And that, as we understand it, resembles more lifelike querying patterns. That the combination of column values in a same table is not necessarily independent. For example, you see on the query on the screen here, for the address table, the address ID is tightly correlated with address line 1 and 2. And let's say if there was another column, let's say the zip code would also be tightly correlated. So this resembles more real-life data querying. There is also another possible correlation here, which is data is fully correlated. And that is a hint to use this specific assumption here. C feedback will be able to analyze which correlation type and model is being used by default, depending on your cardinality estimation version. And if we see again those order of magnitude differences in terms of estimated rows and actual rows, we'll be able to start using other forms of correlation and see if those yield better results. If those are verified, then that becomes the one that's used. Another strategy that the query optimizer uses is called row goal. Row goal is a default strategy when specific types of queries are sent to the database engine. For example, the query you see on the screen here as a top keyword. The top keyword is already hinting, let's say, the database engine that it should only account or estimate to retrieve X amount of rows. Top 1 meaning only one row will be retrieved. Top 100 meaning only 100 rows will be part of the result set. So it is, in essence, a strategy that is default in the database engine to make sure that we read the least amount of data needed to come up with that predefined result set in terms of number of rows. So the row goal will be applied whenever a query has a top keyword or the fast n as a hint, or an in or exists keyword. Those are keywords that, when present in a query, will make the query optimizer look for a row goal strategy. The query optimizer will calculate the number of rows to be read, in this case, to find the required top n rows, top 1 rows in this query, for example. If there is a large percentage of the rows matching the query predicate, and this is an assumption or an estimation based on statistics, then the query optimizer will choose to scan pages to produce the required rows. And once the required rows are scanned, we can move on. In this case, would perhaps mean that we scan very few pages to produce those rows. However, if the data is not uniformly distributed, we might end up scanning a lot more pages than estimated. And that right there is a potential inefficiency of the row goal strategy if estimations are not correct. Historically, we could use, for example, a force seek hint to address this in a plan guide. And there is also a use hint to force disabling the row goal, which is exactly what C feedback would do. If we see there are significant differences, again, between estimated rows and actual rows, and those differences are based upon the usage of the row goal strategy, then C feedback will disable the row goal, which typically would scan, and enable a seek. If it yields a better result, it's verified, then it remains from then on a forced hint in query store that plan will always be used. And if it yields a worse result, then we never persist that in the first place. And so we keep on using whatever the default was used. And the final scenario is containment types. Containment applies to joins. Simple containment was the default for CE70, the so-called legacy CE. And the assumption there was join predicates were fully correlated. In other words, the assumption there was that users would always query for data that actually exists. And so what would happen is, for a join between two tables, an equijoin between two tables, first, the engine would filter the tables and then would calculate the estimation for the join itself. CE 120 and above, however, changed this to so-called base containment. It does not assume correlation between join predicates and their filters. In other words, it means that users might query for data that actually does not exist on the table. So instead, base containment, what it does is, first, the engine will calculate the estimation for the join predicate and then apply the filters on top. So the complete opposite of simple containment. And if you look at the query that you see on the screen here, we have a join between two tables, fact, currency, date, and dim date. And it has a join predicate, and then it has a number of filters in the where clause that can be applied to that join. So containment only applies to joins, as I said, and only if there are filters below the join. So for containment to be present, we need to see a join, an equijoin between two tables, and filters applied to that join, one side or the other or both. If the incoming join estimates are acceptable, meaning they end up being very close to the actual number of rows, because remember that C feedback works based on runtime characteristics. So if the input estimates are acceptable, but the outgoing estimates are bad, meaning the actual number of rows is way different, then it's likely that the containment model is the issue here. And so there is a hint to flip the containment model. And so if it's determined that it's the containment that is the problem, the C feedback will use the opposite containment model to the advantage of your query. So with all these three scenarios, you didn't have to be an expert at cardinality estimation to be able to tackle these scenarios. C feedback will do this for you. Let's see an overview of the C feedback process. First, there's an incoming user query, an eligible query. Eligible meaning that the patterns, the models that we discussed in the past few minutes are identifiable in those queries. And the queries are also repeatable. So the query is incoming and it goes through the query optimizer. And the query optimizer will inquire if there is previous feedback for that specific query. If there is previous feedback, it's stored in the query store. So it will be loaded from the query store. The query will go on to execution and it will return the result set. This means that in essence, instead of the query optimizer having to run through its entire default process, it used the assumption hints and the model hints that were stored in the query store in order to drive a different result from the query optimizer. If feedback does not exist, but the query is eligible, then the query will be tagged for future analysis. And based at that first point in time, based on the defaults from the query optimizer, the query will be sent to execution. Now, if the query was tagged for cardinality model use, meaning if it is eligible for the C feedback, then we'll see which are the model hint variations that are applicable to the pattern that we're seeing in that query. Is it row goal? Is it a correlation difference? It is a containment difference. And then we'll be using subsequent executions of that same query to analyze what are the change strategies that may work best for that specific query. And if C feedback becomes available, meaning that the engine found one or more hints that would be useful to improve that query, again, based on the observation of runtime stats, so between estimated rows and actual rows, it will get that data from the query store, identify a regression, and apply C feedback recommendation for the next execution. And that next execution that your application sent will already use whatever possible changes or hints that will change the model applicable to that query. If it is verified to be a good result, a good outcome, then that will be stored in the query store for subsequent executions. If this validation did not yield good results, then we will back off, as I mentioned earlier. We will not store anything in the query store, and that query from there on until such time when it gets recompiled, for example, will not be eligible for C feedback anymore. And now let's look at a quick demo of C feedback. For this demo, I will be using the TPCH database. And the first step is to enable the query store. As we've seen throughout this session, the query store is becoming a foundation for many of the intelligent database features that we will be developing. We've seen how C feedback will use query store hinting, and therefore it requires that query store is enabled. Just to make sure that everything is a blank slate, I'm also going to clear the query store. And although it's not necessarily needed for this demo, I want to enable automatic tuning. Now, why is this relevant here? Much like it happens with features under the intelligent query processing family, which can interact with each other for the benefit of your workload's performance, the intent is that automatic tuning continues to be, let's say, the final safeguard against any potential regression that other feature may introduce. While we have seen that CE feedback will uphold the do no harm principle, and if it detects that one of its unverified recommendations is actually introducing a regression, it will not persist it. But in the unlikely event that some issue may occur that a recommendation enacted by CE feedback does introduce a regression later, then automatic tuning is there as another gate that can go back to a last known good plan. So these two features can work in tandem to ensure that the intelligent database features don't introduce harm to your workload. I'm also going to clear the procedure cache and drop all clean buffers to ensure that I have a blank slate. And now I'm going to set up Xevent trace that includes the query feedback analysis event, with which we will be able to see the result of the query feedback analysis process and eventually see which hint or hints are being recommended for any given query. So I'm going to create this Xevent session. I need to refresh here. There we go. And the next step will be to set up the environment. Now, at this point in time, the preview has not started yet. I need to enable a couple of trace flags that will not be available after we start the preview, just to enable these two features that work in tandem. In this case, CE feedback, which is reliant upon query store hints. I'm also going to start the Xevent session. And the next step will be to actually look at the data for this session. So now that I have everything set up, I'm going to run this query 15 times so it becomes eligible for CE feedback. Remember that only repeating queries will be eligible for CE feedback. Right now, there's nothing occurring. The query just entered the threshold to become eligible. And if we look at the cached plans, because another consideration is that the query needs to be cached, we can see that my query, the one I ran just now, is cached and it's been used 15 times in this case. Okay, so a recompile event comes in later in time, and the next execution of this query will trigger the process of CE feedback. The query at this point in time is already tagged for CE feedback, so the next execution should do the analysis process itself. And if I go to the live data, that's what I see. In this case, I see that the hint that's being recommended is this assume full independence for filter estimates. Now, I can even take this manually and use it. However, CE feedback will do this automatically for you. So you don't need to be an expert, and you don't need to be hinting all your queries. So the next step, if you recall from the workflow that we've seen earlier, would take that hint that was just found, verify it, and if it was verified successfully, then any subsequent execution, in this case I'm going to run 15 additional times, would in fact apply that hint through query store. From then on, any new incoming execution for that query will use that persisted hint that now sits in query store. I'm going to stop the session now. And this is just a small demo of the power of this feature that is executing automatically, is using your own workload to run through this exercise, and come out on the other side with a better plan for your workloads. As expected, CE feedback will have some supportability artifacts. We've seen one of the X events being used in the demo, and the X events available will allow you to see or to track in which stage any given query feedback is at. The stage where the CE feedback feature has identified one or more hints that may be applicable to a query, and it will submit them for validation. And then you'll be able to see the pre-validation results as well. However, you will also have a catalog view, sys query store plan feedback, which amongst other columns will have a visibility of the current state of any query in the feedback loop that we've seen previously before the demo, and also a JSON column that will have information about essentially what is the CE feedback feature findings for that given query and how much has the query improved based on the observations of runtime statistics when the CE feedback feature was performing its validation. We will begin the preview in early 2021. You may follow the Azure updates to stay tuned when we announce that preview. And if you have feedback about what you've seen today, about other scenarios that you think would be useful to be dealt under CE feedback, we have that email there that you see on the screen, ceffeedback@microsoft.com, and we'll gladly take your feedback. Thank you for attending our session today. You have our Twitter handles here in case you want to get in touch, and enjoy the rest of PASS.